The James Webb Space Telescope, previously known as Next Generation Space Telescope, is a planned space observatory optimized for observations in the infrared, and a scientific successor to the Hubble Space Telescope and the Spitzer Space Telescope. The main technical features are a large and very cold 6.5-meter diameter mirror and 4 specialized instruments at an observing position far from Earth, orbiting the Earth-Sun L2 point. The combination of these features will give JWST unprecedented resolution and sensitivity from long-wavelength visible to the mid-infrared, enabling its two main scientific goals: studying the birth and evolution of galaxies, and the formation of stars and planets. In planning since 1996, the project represents an international collaboration of about 17 countries led by NASA, and with significant contributions from the European Space Agency and the Canadian Space Agency. It is named after James E. Webb, the second administrator of NASA, who played an integral role in the Apollo program. JWST's capabilities will enable a broad range of investigations across many subfields of astronomy. One particular goal involves observing some of the most distant objects in the universe, beyond the reach of current ground and space-based instruments. This includes the very first stars, the epoch of reionization, and the formation of the first galaxies. Another goal is understanding the formation of stars and planets. This will include imaging molecular clouds and star-forming clusters, studying the debris disks around stars, direct imaging of planets, and spectroscopic examination of planetary transits. The mission has a history of major cost overruns and was under review for cancellation by the United States Congress in 2011, after about $3 billion had been spent, and more than 75% of its hardware was either in production or undergoing testing. In November 2011, Congress reversed plans to cancel the JWST and instead capped additional funding to complete the project at $8 billion. Overview: JWST originated in 1996 as the Next Generation Space Telescope with an estimated cost of $500 million, based on generic planning for a successor to Hubble at least as early as 1993. In 2002 it was renamed after NASA's second administrator James E. Webb, noted for playing a key role in the Apollo program and establishing scientific research as a core NASA activity. The telescope is a project of the National Aeronautics and Space Administration, the United States Space Agency, with international collaboration from the European Space Agency and the Canadian Space Agency, including contributions from 15 nations. The prime contractor is Northrop Grumman. Europe's contributions were formalized in 2007 with an ESA-NASA Memorandum of Understanding that includes the Ariane 5 ECA launcher, near-spec instrument, MIRI optical bench assembly, and manpower support for operations. The JWST will orbit around the Earth-Sun L2 Lagrange point, approximately 1,500,000 kilometers beyond the Earth. Objects near this point can orbit the Sun in synchrony with the Earth, which allows the JWST to use one radiation shield, positioned between the telescope and the Sun, to protect it from the Sun's heat and light and the small amount of additional infrared from the Earth. The telescope will be in a very large 800,000-kilometer radius halo orbit around L2, and so will avoid any part of Earth's shadow. From the JWST's position, the Earth will be very close to the Sun's position but not eclipse it, while the Moon will show a tiny crescent phase during its maximum angular distance from the Sun. The telescope is planned for launch on an Ariane 5 rocket on a 5-year mission with a planned launch date in 2018. Comparisons: in contrast to other proposed observatories, most of which have already been cancelled or put on hold, including Terrestrial Planet Finder, Space Interferometry Mission, Laser Interferometer Space Antenna, and the International X-ray Observatory, the JWST telescope is the last big NASA astrophysics mission of its generation to be built. With the cancellation of Project Constellation and the retirement of the Space Shuttle, it is one of NASA's few remaining big space projects. The telescope's delays and cost increases can be compared to the Hubble Space Telescope. When it formally started in 1972, what came to be known as Hubble had a then estimated development cost of $300 million, but by the time it was sent into orbit in 1990, cost about 4 times that. In addition, new instruments and servicing missions increased the cost to at least $9 billion by 2006. A 2006 article in the journal Nature noted a study in 1984 by the Space Science Board, which estimated that a next-generation infrared observatory would cost $4 billion. Other major telescope concepts that have either been cancelled, studied, or are not approaching launch include Maxim, SOFR, SUVO, SPEX, and the aforementioned cancelled TPF, SIM, LISA, and IXO. Development. JWST is the maturation of the next-generation space telescope plans. Some previously floated concepts include an 8-meter aperture, orbit of 3 astronomical units and Nexus precursor telescope mission. A focus on the near to mid-infrared was preferred for 3 main reasons. High redshift objects have their visible emissions shifted into the infrared. Cold objects such as debris disks and planets emit most strongly in the infrared, and this band is very hard to study from the ground or by existing space telescopes such as Hubble. JWST has a planned mass about half of Hubble, but its primary mirror has a collecting area about 5 times larger. It uses about 3 grams of gold per mirror. The JWST is oriented towards near-infrared astronomy, but can also see orange and red visible light as well as the mid-infrared region, depending on the instrument. Early development work for a Hubble successor between 1989 and 1994 led to the High-Z telescope concept, a fully baffled 4-meter aperture infrared telescope going out to 3 AU in its orbit. The distant orbit helped reduce light noise from zodiacal dust. In the faster, better, cheaper era in the mid-1990s, NASA leaders pushed for a space telescope with low cost and 8-meter primary mirror diameter. The result was plans for a NGST for $500 million, 8-meter aperture, and located at L2. By 2002, as the concept matured into more of a technical reality, it was reduced to 6 meters aperture and the cost was estimated at around $2.5 billion. Concepts for the design were fielded from Goddard Space Flight Center, Ball Aerospace, Lockheed Martin, TRW. In 2002, TRW was bought by Northrop Grumman. Understanding goals, JWST is the formal successor to the Hubble Space Telescope, but since its primary emphasis is on infrared observation, it is equally fair to consider it a successor to the Spitzer Space Telescope. In fact, JWST will far surpass both those telescopes, being able to see many more and much older stars and galaxies. Observing in the infrared is a key technique for achieving this, because it better penetrates obscuring dust and gas, allows observation of dim cooler objects, and because of cosmological redshift. Dust penetration, comparing the 2 images of the Carina Nebula taken with the HST, though both images are of the same astronomical object, the top image was photographed utilizing the visible spectrum whereas the bottom image was taken in the infrared using the HST's WFC3 upgrade. Many more stars can be counted in the bottom image than in the same location of the top image. This demonstrates infrared observation's ability to penetrate the obscuration due to gas and dust that blocks much of the seen invisible spectrum image. Infrared astronomy can penetrate dusty regions of space, such as molecular clouds where stars are born, the circumstellar disks that give rise to planets, and the cores of active galaxies which are often cloaked in gas and dust. Cool objects. Furthermore, relatively cool objects emit their radiation primarily in the infrared, as described by Planck's law. As a result, most objects that are cooler than stars are better studied in the infrared. This includes the clouds of the interstellar medium, the failed stars called brown dwarfs, planets both in our own and other solar systems, and comets and Kuiper belt objects. The distant universe, looking to galaxy clusters, quasars, and gamma-ray bursts, the most distant objects viewable are also the youngest, that is, they were formed closer in time to the Big Bang. Their light has taken billions of years to reach us. Because the universe is expanding, as the light travels it becomes red-shifted and these objects are therefore easier to see if viewed in the infrared. JWST's infrared capabilities are expected to let it see all the way to the very first galaxies forming just a few 100 million years after the Big Bang. In addition, JWST's advanced spectrographic instruments and a large mirror array will enable it to further probe Mars and the outer planets. Mission. The JWST's primary scientific mission has four main components: to search for light from the first stars and galaxies that formed in the universe after the Big Bang, to study the formation and evolution of galaxies, to understand the formation of stars and planetary systems, and to study planetary systems and the origins of life. All of these jobs can be done more effectively by analyzing near-infrared light rather than light in the visible part of the spectrum. For this reason, the JWST's instruments will not measure visible or ultraviolet light like the Hubble telescope, but will have a much greater capacity to collect infrared light. In its present design, the JWST will detect a range of wavelengths from 0.6 to 28 micrometers. Due to a combination of redshift, dust obscuration, and the low temperatures of many of the sources to be studied, the JWST must be able to measure infrared light with a very high degree of precision. To ensure that infrared emissions coming from the telescope or its instruments do not interfere with these observations, the entire observatory must operate at a very low temperature. Moreover, it must be well shielded from radiation coming from the Sun, the Earth and the Moon. To accomplish this, the JWST incorporates a large metallized fan-fold sunshield, which will unfurl to block infrared radiation and allow the telescope to radiatively cool down to roughly 40 K. The telescope's location at the Sun-Earth L2 Lagrange point ensures that the Sun, Earth, and Moon all occupy roughly the same position relative to the telescope, and thus make the operation of this shield possible. The observatory is currently scheduled to be launched by an Ariane 5 from Guyana Space Center Kaohsiung, French Guiana, into an L2 orbit with a launch mass of approximately 6.2 tons. After a commissioning period of approximately 6 months, the observatory will begin the science mission, which is expected to last a minimum of 5 years. The potential for extension of the science mission beyond this period exists, and the observatory is being designed accordingly. Orbit. The orbit of the JWST will be an elliptical orbit around the semi-stable second Lagrange point, or L2. The Earth-Sun L2 point, about which the Webb telescope will orbit, is 1,500,000 kilometers from the Earth, around 4 times farther than the distance between the Earth to the Moon. At such a great distance, the Webb telescope would be more difficult to service after launch than the Hubble telescope. Nevertheless, a docking ring was added to the design in 2007 to facilitate this possibility either by a robot or future crewed spacecraft such as the Orion MPCV. Normally, an object circling the Sun further out than the Earth would take more than 1 year to complete its orbit. However, the balance of gravitational pull at the L2 point means that JWST will keep up with the Earth as it goes around the Sun. The combined gravitational forces of the Sun and the Earth can hold a spacecraft at this point, so that in theory it takes no rocket thrust to keep a spacecraft in orbit around L2. In reality, the stable point is comparable to that of a ball balanced upon a saddle shape. Along one direction, any perturbation will drive the ball toward the stable point, while in the crossing direction the ball, if disturbed, will fall away from the stable point. Thus some station keeping is required, but with little energy expended. Sun shield protection. As the JWST must be kept very cold to make accurate observations of distant astronomical objects, it has been designed with a large sun shield that blocks light and heat from the Sun. In order for such a shield to work properly, the Sun's rays must be constantly coming from the same direction. To achieve this outcome, JWST will be put into a relatively large halo orbit around L2. From the L2 point, the Earth constantly shades 1/3 of the Sun's light as it periodically wobbles about the Earth-Moon barycenter. Occasionally lunar eclipses will partially obscure more of the solar disk. However, the radius of the telescope's orbit around L2 will be so large that neither the Earth nor Moon will eclipse the Sun, allowing the shield to deal with a relatively constant sunlight environment. This was considered to be more important than attempting to utilize the Earth's shadow to block some of the sunlight, in an orbit nearer the exact L2 point. JWST's sunshield, made of polyamide film, has membranes coated with aluminum on one side and silicon on the other. The Sun shield is designed to be folded 12 times so it will fit within the Ariane 5 rocket's 4.57 ma, 16.19 m shroud. Once deployed at the L2 point, it will unfold to 12.2 ma, 18 m. The Sun shield was hand-assembled at Mantech in Huntsville, Alabama before it was delivered to Northrop Grumman in Redondo Beach, California for testing. Optics and instruments. Optical Design, JWST's primary mirror is a 6.5-meter diameter gold-coated beryllium reflector with a collecting area of 25 am2. This is too large for contemporary launch vehicles, so the mirror is composed of 18 hexagonal segments, which will unfold after the telescope is launched. Image plane wavefront sensing through phase retrieval will be used to position the mirror segments in the correct location using very precise micromotors. Subsequent to this initial configuration, they will only need occasional updates every few days to retain optimal focus. This is unlike terrestrial telescopes like the Keck, which continually adjust their mirror segments using active optics to overcome the effects of gravitational and wind loading, and is made possible because of the lack of environmental disturbances to a telescope in space. JWST's optical design is a 3-mirror anastigmat, which makes use of curved secondary and tertiary mirrors to deliver images that are free of optical aberrations over a wide field. In addition, there is a fast steering mirror, which can adjust its position many times a second to provide image stabilization. Ball Aerospace and Technologies Corporation is the principal optical subcontractor for the JWST program, led by prime contractor Northrop Grumman Aerospace Systems, under a contract from the NASA Goddard Space Flight Center, in Greenbelt, Maryland. 18 primary mirror segments, secondary, tertiary and fine steering mirrors, plus flight spares have been fabricated and polished by Ball Aerospace based on beryllium segment blanks manufactured by several companies including Axe, Brush-Wellman, and Tinsley Laboratories. As of June 2011, the first set of 6 fully completed mirror segments, including rigid supporting frames and cryogenic actuators, was undergoing final testing at NASA Marshall Space Flight Center, and testing all of the remaining mirrors was completed by December 2011, 2 months ahead of schedule. Scientific instruments. The Integrated Science Instrument Module contains 4 science instruments and a guide camera. Near-infrared camera is an infrared imager which will have a spectral coverage ranging from the edge of the visible through the near-infrared. NIR-arm will also serve as the observatory's wavefront sensor, which is required for wavefront sensing and control activities. NIR-arm is being built by a team led by the University of Arizona, with principal investigator Marcia Riek. The industrial partner is Lockheed Martin's Advanced Technology Center located in Palo Alto, California. Near-infrared spectrograph will also perform spectroscopy over the same wavelength range. It is being built by the European Space Agency at ESTEC in Noordwijk, Netherlands. The leading development team is composed of people from Astrium, Otto Braun in Friedrichshafen, Germany, and the Goddard Space Flight Center. With Pierre Ferraut as NearSpec project scientist. The NearSpec design provides 3 observing modes, a low-resolution mode using a prism, a 0 to 1000 multi-object mode and a 0 to 2700 integral field unit or long-slit spectroscopy mode. Switching of the modes is done by operating a wavelength preselection mechanism called filter wheel assembly and selecting a correspondent dispersive element using the grating wheel assembly mechanism. Both mechanisms are based on the successful isophot wheel mechanisms of the Infrared Space Observatory. The multi-object mode relies on a complex micro-shutter mechanism to allow for simultaneous observations of hundreds of individual objects anywhere in NearSpec's field of view. The mechanisms and their optical elements are being designed, integrated and tested by Carl Zeiss Optronics GmbH of Oberkochen, Germany, under contract from Astrium. Mid-infrared instrument will measure the mid-infrared wavelength range from 5 to 27 micrometers. It contains both a mid-IR camera and an imaging spectrometer. MIRI is being developed as a collaboration between NASA and a consortium of European countries, and is led by George Riek and Gillian Wright. MIRI features similar wheel mechanisms as NGST, which are also developed and built by Carl Zeiss Optronics GmbH under contract from the Max Planck Institute for Astronomy, Heidelberg. The completed optical bench assembly of MIRI was delivered to Goddard in mid-2012 for eventual integration into the ISIM. Fine Guidance Sensor, led by the Canadian Space Agency under project scientist John Hutchings, is used to stabilize the line of sight of the observatory during science observations. Measurements by the FGS are used both to control the overall orientation of the spacecraft and to drive the fine steering mirror for image stabilization. The Canadian Space Agency is also providing a near-infrared imager and slitless spectrograph module for astronomical imaging and spectroscopy in the 0.8 to 5 micrometer wavelength range, led by principal investigator Rena Copyright-Doyon at the University of Montreal. Because the NIRISS is physically mounted together with the FGS, they are often referred to as a single unit, but they serve entirely different purposes, with one being a scientific instrument and the other being a part of the observatory's support infrastructure. NIRAM and MIRI feature starlight blocking coronagraphs for observation of faint targets such as extrasolar planets and circumstellar disks very close to bright stars. The infrared detectors for the NIRAM, NIRSpec, FGS, and NIRISS modules are being provided by Teledyne Imaging Sensors. Construction and engineering. NASA's Goddard Space Flight Center in Greenbelt, Maryland, is leading the management of the observatory project. The project scientist for the James Webb Space Telescope is John C. Mather. Northrop Grumman Aerospace Systems serves as the primary contractor for the development and integration of the observatory. They are responsible for developing and building the spacecraft element, which includes both the spacecraft bus and sun shield. Ball Aerospace has been subcontracted to develop and build the optical telescope element. Goddard Space Flight Center is also responsible for providing the integrated science instrument module. NASA is considering plans to add a grapple feature so future spacecraft might visit the observatory to fix gross deployment problems, such as a stuck solar panel or antenna. However, the telescope itself would not be serviceable, so that astronauts would not be able to perform tasks such as swapping instruments, as with the Hubble telescope. Final approval for such an addition was to be considered as part of the preliminary design review in March 2008. Most of the data processing on the telescope is done by conventional single-board computers. The conversion of the analog science data to digital form is performed by the custom-built sidecar ASIC. It is said that the sidecar ASIC will include all the functions of a 20-pound instrument box in a package the size of $0.50, and consume only 11 milliwatts of power. Since this conversion must be done close to the detectors, on the cool side of the telescope, the low power use of this IC will be important for maintaining the low temperature required for optimal operation of the JWST. Ground support and operations. The Space Telescope Science Institute in Baltimore, Maryland has been selected as the Science and Operations Center for JWST. In this capacity, STSCI will be responsible for the scientific operation of the telescope and delivery of data products to the astronomical community. Data will be transmitted from JWST to the ground via NASA's Deep Space Network, processed and calibrated at STSCI, and then distributed online to astronomers worldwide. Similar to how Hubble is operated, anyone, anywhere in the world, will be allowed to submit proposals for observations. Each year several committees of astronomers will peer review the submitted proposals to select the programs to observe in the coming year. The authors of the chosen proposals will typically have 1 year of private access to the new observations, after which the data will become publicly available for download by anyone from the online archive at STSCI. Program status. A review of the program released in August 2011, said the cost for the telescope and 5 years of operations will be $8.7 billion with a planned launch in 2018. Of that price about $800 million is for the 5 years of operations. The Webb will be launched from Arianespace's ELA-3 launch complex at European Spaceport located near Kourou, French Guiana. The planned launch vehicle is an Ariane 5 ECA with a cryogenic upper stage. History of the program. Cost growth revealed in spring 2005 led to an August 2005 replanning. The primary technical outcomes of the replanning were significant changes in the integration and test plans, a 22-month launch delay, and elimination of system-level testing for observatory modes at wavelengths shorter than 1.7 micrometers. Other major features of the observatory were unchanged. Following the replanning, the program was independently reviewed in April 2006. The review concluded the program was technically sound, but that funding phasing at NASA needed to be changed. NASA rephased its JWST budgets accordingly. In the 2005 replan, the lifecycle cost of the project was estimated at about $4.5 billion. This comprised approximately $3.5 billion for design, development, launch and commissioning, and approximately $1.0 billion for 10 years of operations. ESA is contributing about $300 million, including the launch, and the Canadian Space Agency about $39 million Canadian. As of May 2007, costs were still on target. In January 2007, 9 of the 10 technology development items in the program successfully passed a non-advocate review. These technologies were deemed sufficiently mature to retire significant risks in the program. The remaining technology development item completed its technology maturation milestone in April 2007. This technology review represented the beginning step in the process that ultimately moved the program into its detailed design phase. In March 2008, the project successfully completed its preliminary design review. In April 2008, the project passed the non-advocate review. Other past reviews include the Integrated Science Instrument Module review in March 2009, the Optical Telescope Element review completed in October 2009, and the Sun Shield review completed in January 2010. In April 2010, the telescope passed the technical portion of its mission-critical design review. Passing the MCDR signified the integrated observatory will meet all science and engineering requirements for its mission. The MCDR encompassed all previous design reviews. The project schedule underwent review during the months following the MCDR, in a process called the Independent Comprehensive Review Panel, which led to a replan of the mission aiming for 2015, but as late as 2018. By 2010, cost overruns were impacting other programs, though JWST itself remained on schedule. By 2011, the JWST program was in the final design and fabrication phase. As is typical for a complex design that cannot be changed once launched, there are detailed reviews of every portion of design, construction, and proposed operation. New technological frontiers have been pioneered by the program, and it has passed its design reviews. In the 1990s, it was unknown if a telescope so large and light was possible. In April 2011, cryogenic testing of a sixth mirror array began. This test is to ensure the mirrors perform to specifications at the temperatures they will encounter. On June 16, 2014, the ISIM or Integrated Science Instrument Module of the JWST was lowered by a 30-foot cable into Goddard's Space Environment Simulator for a 4-month-long thermal vacuum test. Even with the funding for the telescope secured, the program's status remains controversial while the telescope components are being completed. Reported cost and schedule issues. In June 2011, it was reported that the Webb telescope will cost at least 4 times more than originally proposed, and launch at least 7 years late. Initial budget estimates were that the observatory would cost $1.6 billion and launch in 2011. NASA has now scheduled the telescope for a 2018 launch. A 2013 price estimate put the cost at $8.835 billion. Some scientists have expressed concerns about growing costs and schedule delays for the Webb telescope, which competes for scant astronomy budgets and thus threatens funding for other space science programs. A review of NASA budget records and status reports by journalists at Florida Today show the Webb Observatory is plagued by many of the same problems that have plagued several other major NASA projects. Mistakes included underestimates of the telescope unregistered trademark cost that failed to budget for expected technical glitches, and failure to act on warnings that budgets were being exceeded, thus extending the schedule and increasing costs further. Proposed U.S. withdrawal. On July 6, 2011, the United States House of Representatives Appropriations Committee on Commerce, Justice, and Science moved to cancel the James Webb project by proposing an FY 2012 budget that removed $1.9 billion from NASA's overall budget, of which roughly one-quarter was for JWST. This budget proposal was approved by subcommittee vote the following day. However, in November 2011, Congress reversed plans to cancel the JWST and instead capped additional funding to complete the project at $8 billion. The committee charged that the project was billions of dollars over budget and plagued by poor management. The telescope was originally estimated to cost $1.6 billion, but the cost estimate grew throughout the early development, reaching about $5 billion by the time the mission was formally confirmed for construction start in 2008. In summer 2010, the mission passed its critical design review with excellent grades on all technical matters, but schedule and cost slips at that time prompted U.S. Senator Barbara Mikulski to call for an independent review of the project. The independent comprehensive review panel chaired by Jay Gassani found that the earliest launch date was in late 2015 at an extra cost of $1.5 billion. They also pointed out that this would have required extra funding in FY 2011 and FY 2012 and that any later launch date would lead to a higher total cost. Because the runaway budget diverted funding from other research, the science journal Nature described the James Webb as the telescope that ate astronomy. However, termination of the project as proposed by the House Appropriation Committee does not provide funding to other missions, as the JWST line is simply terminated, with the funding simply leaving astrophysics entirely. The American Astronomical Society issued a statement in support of JWST in 2011, as did Maryland U.S. Senator Barbara Mikulski. A number of editorials supporting JWST appeared in the international press during 2011 as well. Public displays and outreach. A large telescope model has been on display at various places since 2005, in the United States at Seattle, Washington; Colorado Springs, Colorado; Greenbelt, Maryland; Rochester, New York; Manhattan, New York; and Orlando, Florida; and elsewhere at Paris, France; Dublin, Ireland; Montreal, Canada; Hatfield, United Kingdom; and Munich, Germany. The model was built by the main contractor, Northrop Grumman Aerospace Systems. In May 2007, a full-scale model of the telescope was assembled for display at the Smithsonian's National Air and Space Museum on the National Mall, Washington, D.C. The model was intended to give the viewing public a better understanding of the size, scale and complexity of the satellite, as well as pique the interest of viewers in science and astronomy in general. The model is significantly different from the telescope, as the model must withstand gravity and weather, so is constructed mainly of aluminum and steel, measuring approximately 24A, 12A, 12am and weighs 5.5 tons. The model was on display in New York City's Battery Park during the 2010 World Science Festival, where it served as the backdrop for a panel discussion featuring Nobel Prize laureate John C. Mather, astronaut John Grunsfeld and astronomer Heidi Hammel. In March 2013, the model was on display in Austin, Texas for SXSW 2013. Images. Partnership. NASA, ESA and CSA have collaborated on the telescope since 1996. ESA's participation in construction and launch was approved by its members in 2003 and an agreement was signed between ESA and NASA in 2007. In exchange for full partnership, representation and access to the observatory for its astronomers, ESA is providing the near-spec instrument, the optical bench assembly of the MIRI instrument, an Ariane 5 ECA launcher, and manpower to support operations. The CSA will provide the fine guidance sensor and a near-infrared imager slitless spectrograph plus manpower to support operations. Participating countries, notes. References. Further reading, Jonathan P. Gardner. A. L. The James Webb Space Telescope. Space Science Reviews, 484 euro 606 are the formal case for the JWST Science, plus some implementation. JWST Primer, JWST Glossary, External links, Official website, James Webb Space Telescope Mission Profile by NASA's Solar System Exploration, Progress Report, AIAA 2004-5986, JWST Observatory Architecture and Performance, AIAA 2006-5593, Development of JWST's ground systems using an open adaptable architecture, JWST Gallery on FLICKR, JWST Mirrors Overview at NASA, Ecclestone, Paul. Space Camera. Backstage Science. Brady Heron A, Video Search for Life in the Universe NASA. Science Instrument Teams, NIRAM homepage at Arizona, MIRI homepage at Arizona, MIRI homepage at UK Astronomy Technology Centre. Background, Stephen V. W. Becker. The Hubble JWST Transition, a Policy Synopsis. Papers per STCI, E.P. Smith. Infrared Astronomy and NGST. NASA Goddard Space Flight Center, Cost Overruns Put Squeeze on Hubble. Unregistered Trademark S. Successor. New Scientist, About Third Mirror, James Webb Space Telescope, Project Meeting Commitments but Current Technical, Cost, and Schedule Challenges Could Affect Continued Progress. Government Accountability Office, January 2014, The Next Great Observatory. Assessing the James Webb Space Telescope, hearing before the Committee on Science, Space, and Technology, House of Representatives, 112th Congress, First Session, Tuesday, December 6, 2011.